Okay, we are on section 5.1. And we are talking about basic concepts of probability. Okay? If you want to type instead of write, you can. That's up to you. There are some, math stuff going on in there, but for the most part, it is kind of, you can type it up. The things I started off with on this, we are going to construct sample spaces. We are going to compute and interpret probabilities. And then we are going to approximate probabilities by using the empirical method. And you guys know we talked about empirical method in Unit 1. Okay? We do have a couple of definitions, such as what is a probability experiment. Okay, and a probability experiment is, of course, an experiment in which we do not know what any individual outcome will be, but we do know how long a series of repetitions will come out. Okay? Examples of probability experiments are a coin toss, and rolling a die. Guys, when we say dice, that's plural for die. Okay? It's more than one. It's not a roll of dice. If you're rolling dice, it's two or more die. Okay? The probability of an event is the proportion of times the event occurs in the long run. As a probability experiment, is repeated over and over. And guys, I don't like writing definitions any more than you do, but it has been proven that in the homework and on the test, they love to talk about vocabulary. That's just, and to me, that's always frustrated me because it's a math class. Why am I doing vocabulary in math class? But since it's new, We also have the definition of the law of large numbers. Says that as a probability experiment, is repeated again and again, the proportion of times that a given event occurs will approach its probability. And I'll explain that in just a second, because it sounds like we talked in circles. The law of large numbers is another way to state our definition of probability. Okay? Okay, so what that means is if we go, law of large numbers just means, okay, I'm going to flip a coin. And you know you have 50-50 chance as far as getting a head, getting a tail. Okay? So let's flip a coin 3 times. So the probability of getting a head or getting a tail, it should be 50%, but it may not be with just 3 flips, okay? You might get a head all 3 times with 3 flips. Well, that's not 50% on the tail, 50% on the head. But what the law of large numbers says, if we keep flipping over and over and over and over and over again, 100 times, 200 times, 500 times, 1,000 times, eventually that's going to start to even out. And you will see that we will get heads 50% of the time, and we will get tails 50% of the time. If you do that flip, and it's a fairly weighted coin, you do know, guys, those of you that do gamble, you know that you can weight dice, and you can have an unfair coin too. You can actually make a coin unfair by if you'll grind off part of like if you have a nickel or a quarter, and it's evenly weighted the way it's made. But if you sand or grind off on one side, then it's lighter on that side, so it's going to flip with the other side down all the time. So let's say you sand or grind on the head, because that sticks out the most, the head of a coin. You grind that down. When you flip it, it's going to land heads up more times than not. And so you play with that coin so you know to bet heads more, because the heavy side is going to fall down. It's the same way with a die. If you're rolling dice, you can, the dice have the holes in them, like each side of a die has 1, 2, 3, 4, 5, 6. If you'll take some people that cheat, they'll carve out that hole a little bit more. It used to be more prevalent when they were made out of wood. If you carve those holes a little bit more out and then paint back over it, then it's not weighted evenly on each side. So that's why you'll see in the problems, they'll talk about a fair die or a fair coin. That's what they mean. You can actually make them unfair if you cheat, okay? A sample space contains all the possible outcomes of a probability experiment. Okay? And that does bring us to example 1. Example 1 states, describe a sample space for each of the following experiments. Okay? A, the toss of a coin. Okay, so it wants us to describe the sample space of the toss of a coin. Well, guys, a sample space just contains all the possible outcomes of a probability experiment. They list this in brackets. If I flip a coin, what are the possibilities I could get? What can I actually get? Like I flip it and what, a head or a tail, right? So the sample space is heads or tails. Okay? B, the roll of a die. Well, okay, now I'm not talking a D&D Dungeons and Dragons die. I'm talking normal, we roll a die. Okay, like we roll dice in Monopoly. Okay, like one of those. Okay? How many, what could you roll? When you roll that die, what could you roll? 1 through 6, okay? So that's your sample space. 1, 2, 3, 4, 5, 6. That's all it's asking you guys when you have a sample space is what could you roll, what could you draw, what could come up as an answer, okay? C, they try to change it up a little, selecting a student at random from a list of 10,000 students at a large university. Okay, selecting a student at random from a list of 10,000 students at a large university. You can't list this sample space in a bracket. You don't know the names, nor do you have the time to list 10,000 different students. That's what we have databases for, and computers run that, okay? So we just say the sample space consists of each of the 10,000 students. Because everybody is just as likely to get drawn as anybody else. Okay? D, last part of example 1. Selecting a simple random sample of 100 students from a list of 10,000 students. Okay, so they changed this one up a little bit. Okay? So what they're doing is they've got 10,000 students. They're going to select 100 at a time. Put those back. They'll select 100 different ones at a time. Put those back. Select a different 100. So our sample space consists of this sample space. Consists of every group of 100 students that can be chosen from the population of 10,000 students. Okay? So it's every possible random sample of size 100, which eventually we will learn how to calculate that, but I mean, it's a lot. It's a lot. Okay? Couple more definitions here. An event is an outcome or a collection of outcomes from a sample space. Okay? You need to know when they write P parentheses A, and we say P of A, okay, is how it's read, P of A, denotes the probability of the event A. And we're going to practice these guys. And finally, oh, I need to flip the page. I might flip the page. Because this one's longer. We actually define P of A. Y'all good? Okay, you're good. I should have lassoed and just put it on the other page. Actually, I do need to. It would be better if he was over here. Okay, I'm gonna flip it and I'm gonna put him on the other page. Oh, okay. Because it doesn't make sense for me to. I should have done that to begin with. P of A denotes the probability of the event A, and if. So we're going to define that. A sample space has n equally likely outcomes and an event A has K outcomes, then the probability of A equals the number of outcomes in A divided by the number of outcomes in the sample space. And that's a very wordy way to define probability. It's a lot easier if we just work an example. So, let's look at example 2. Example 2 states a fair die, see, it's fair, nobody been whittling on it, is rolled. Find the probability that an odd number comes up. Okay? So we're looking for the probability of an odd number. All right, so let's think about what's my sample space? 1 through 6, right? It is, I need to scoot that down a little bit. It's going to be 1, 2, 3, 4, 5, 6, okay? Now, notice that's the bottom part of your fraction on probability. It says the number of outcomes in the sample space. There are a possibility of 6 different answers. When I roll it, I could get 6 different things, right? I could get a 1, I could get a 2, 3, 4, 5, 6. Okay, so that's the total. We got a 6 there on the bottom in my denominator. Let me use appropriate terminology. Okay, now I want an odd number. Okay, well, what are my possible odd numbers that I could roll? 1, 3, and 5. So I have 3 chances to get an odd number, right? With each roll. 3 out of 6. That's really 1/2. So the probability of getting an odd number is 1/2. 1 out of 2. Right? 50%. And we'll talk about changing that to percent later. They might also, some of the examples, they leave it as 1/2. Some of them, they'll write it as 0.5. That leads me to believe your homework will take either. Okay? But 1/2 is you got a 50-50 shot, right, of getting an odd number. Makes sense, guys. We got 1, 2, 3, 4, 5, 6. We got 3 evens. We got 3 odds. 50-50 shot. You're going to roll an odd, right? Okay? Let's do, that was example 2. Let's do example 3. I need to. Example 3. In the Georgia Cash 4 lottery game, in the Georgia Cash 4 lottery game, a winning number between 0,000 and 9999 is chosen at random. With all the possible numbers being equally likely. Okay? What is the probability that all 4 digits of the winning number are the same? Let's just say all 4 digits are the same. Okay. So, here's how this goes. It starts off, you could choose, because it could pop up 0, 0, 0, 0. Then it goes 1. Then it goes 2, 3, 4, 5, 6, all the way up to 9,999. And we want the probability that all 4 numbers are the same. Okay? Well, let's give an example of all 4 numbers being the same. You can find them. We can find them, okay? Tell me one of the numbers that we get if all 4 numbers are the same. Yeah. So like 2, 2, 2, 2. 3, 3, 3, 3. Of course, we got our 1, 1, 1, 1, 0, 0, 0, 0. All the way up to 9, 9, 9, 9, right? 5, 5, 5, 5, 6, 6, 6, 6, 7, 7, 7, 7, 8, 8, 8, 8, 9, 9, 9, 9. How many chances right there do I have? Are there 9? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. Okay, but that will help you answer the next part because we had to count 0, 0, 0, 0, right? If I had started with 1, 1, 1, 1, 1, 1, 1, 1 and went to the 9, 9, 9, 9, there would have been 9. But I've got the 0, 0, 0, 0 in there, right? Okay, so you know on the top is how many I could actually possibly get. Well, there's 10. Now the bottom is the entire number in the sample space. How many different numbers are there? Close. If I had started with 0, 0, 0, 1, if I'd started with 1, I would have 9,999. But I actually started with 0, 0, 0, 0, so there's 10,000. Good. That's why I'm glad you answered 9 on the first one. So that played right into it's going to be 10,000 versus 9,999. So the probability of all 4 of them being exactly the same is 10 out of 10,000, which is really 1 out of 1,000, which is 0.001. That's less than a 1% chance, guys. Because to turn that into a percent, what we do? Move the decimal 2 places to the right? So it's a 0.1% chance. So I would not suggest that you buy a ticket and make the number the same. It's not, you don't have a real good chance there, okay? This is very important. They do ask questions. They ask homework questions about this, and I promise you there'll be some test question about it. Rules, there's probably even a question on your final exam about this. Rules for the value of a probability. A probability can never be negative, and a probability can never be greater than 1. Okay? Can never be negative. Can't be less than 0, guys. And it can't be greater than 1. Okay? If A cannot occur, then the probability of A equals 0. If A is certain to occur, then the probability of A equals 1. Okay. I will put example 4 on the next page because it is long. It's not hard, it's just long. Okay. Example 4 states a penny, a nickel, and a dime are tossed. Okay? Denoting a head by H and a tail by T, we can denote these 3 tosses in order. Okay. I'll actually write and then move. Example 4. A penny, a nickel, and a dime are tossed. Denoting a head by H, a tail by T, we can denote these 3 tosses in order. Okay? Part A does ask me, what is the probability? That there are exactly 2 heads. Okay. We want exactly 2 heads. So we got a penny, we've got a nickel, and we've got a dime. Well, the first thing we need to figure out is what I could have, right? Okay, so I could have a head. If this is like, okay, I'm gonna list, I'm gonna circle and I'm gonna move this over here. Give me just a second. Okay. Okay, so we're flipping a penny, a nickel, and a dime, right? Now, I could get real lucky and I could have heads, right? That's one combination. What we're doing right now is we're listing all the different combinations we could get. We could get a head, and a tail, right? We could get a head, a tail, and a head. Or we could get a tail, a head, and a head. You agree? Hey. We're just writing notes, Michael, and then I'm going to post them afterwards. Okay? Oh, wait, hold on. Yeah, you should have stared at me. Yes, here's your test. I'm going to there you go. Sorry. Okay, now, so we could have, there's 4, but there's more, right? Because all I've listed is if that penny is coming up heads. Look, penny came up heads every time there. I changed nickel and dime, but penny was always head. And pretty much what I did, and here's how I keep track of it in my head. I start off with all the heads, and then I change 1 to tail. And then I move that tail, well, we do have 1 tail. I made the penny a tail at the end. And then I just move that tail to all the spaces. Okay? Now, when I get back to that penny having a tail, well, now I list all my tails. So I could have tail, 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 right? Could have 3 tails. I could have a tail, tail, head. I could have a tail, head, tail. And so now see how the head's moving around? And then I could have a, what? Head, tail, tail. So how many possible outcomes are there? What's my sample space? How many are there? 8, that's correct. And we want the probability of getting exactly 2 heads. Okay? Well, there's a total of 8 possibilities. That's what you listed on the side right there, was the possibilities that you could flip. Okay? Now we go through and we want exactly 2 heads. Okay? Only 2 heads. So this second one is a head, head, tail. That's exactly 2 heads, right? Then we could have the third one, which is a, what? Head, tail, head. Okay? Then the fourth one has 2 heads. It didn't say they had to be in a row. It didn't say who had the heads. It says you got to have exactly 2 heads. Do we have another one with exactly 2 heads? No. So, that's 3 out of 8. And you can leave that as a fraction, like I said. If you want to put it in your calculator and get a decimal, you can. Or you can leave it 3 out of 8. I'm going to put B right underneath here because it deals with this same sample space that we have, okay? It says what is the probability that all 3 tosses are the same. Okay? So I want the probability that all 3 are the same. Okay, guys. Well, the amount in your sample space, your combinations is the same. You don't have to produce that again. There's 8, right? There's 8 different possibilities that we could get. So now we just need to look back at that sample space and count how many were there all 3 the same. Well, I kind of gave that away when I was doing it, right? Because I was like, oh, I start off with everybody being heads, and then I finish with everybody being tails. So how many are there? 2. I can get head, 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 or I can get tail, 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 right? But all 3 of them are the same. So that gives me 2 out of 8, which is 1 out of 4, which is 0.25. Okay? So pretty much you have a 25% chance of getting tail, 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 or head, head, head. Getting them both as all 3 the same. Okay? C. What is the probability that the penny comes up heads? Okay, we don't care. We don't care what happens to the nickel and the dime. We just need the penny to come up heads. We want the probability that penny is heads. Okay? Let me, what color? I'll put a little star by it. Okay? So penny's heads, I'll circle it. There's 1, penny's heads 2, penny's heads 3, and penny's heads 4, right? You're looking where the penny is ahead. Doesn't matter about nickel and dime. They can be whoever. But you want penny as heads. That's going to give me, what did I get, 4 out of my total, which was 8. So that's just 1/2, right? Or 0.5. And then D, last part for this question, this example, what is the probability that the penny and the dime come up the same? Okay, so penny and the dime have to come up the same. All right, penny's my first column, dime is my last column. So that means they could be a head-head or they could be a tail-tail, right? Okay, let me change, I'll use red. So that first one's pretty good, right? I got a head and a head. Penny and my dime are the same. Okay, row 2, no. Row 3 looks good. He's a head and a head. Okay. 4's a no. 5, we like 5. So a tail and a tail. Okay. 6 is a no-go. 7, he looks good. There's a tail and a tail. And then 8 is head-tail. Okay, so it's the red. So I'm looking for a head in the beginning and a head in the end, right? Or a tail in the beginning and a tail in the end. Okay, so we can say that the probability of penny and dime are the same. Well, there's total of 8 possibilities. Not 4. There's total of 8 possibilities. At least you were the only one that saw that, Raina. It's Monday. 8 possibilities, and how many reds do I have? I had 4, right? So that gives me 4 out of 8, which is 1/2, which is 0.5, which is 50%. Okay? Not bad, right? Let's see how long. Okay, we can fit example 5 in. All right, example 5. A penny and a nickel are tossed. Each is a fair coin, which means that heads and tails are equally likely. And Michael, we did discuss how a coin can be made unfair and a die can also, but I'm figuring you kind of already know that, so yeah. So they tell us each is a fair coin, which means that heads and tails are equally likely. Okay, it wants me to A, construct a sample space. Containing equally likely outcomes. Each outcome should specify the results for both coins. Okay, and all we're going to do, guys, is pretty much make a T-chart. We're going to make the same kind of chart that we did up there, but just with a penny and a nickel. And we make it look a little prettier, okay? So we say penny. And we say nickel. Okay. And I know that I could flip a head and a head, right? I could flip a head or a tail. Or I could flip a tail or a head. Or I could flip a tail or a tail. Okay? That's your sample space. You constructed it. You're good to go. B says find the probability that one coin comes up heads and the other comes up tails. Okay? Find the probability that one coin comes up heads and the other comes up tails. So you don't want a head or a tail. It's got to be head tail head, right? Okay, they've got to be opposite. Okay, they can't be the same. So if I look back up at my sample space, which I made, I can have pennies a head, nickels a tail, or I can have pennies a tail, nickels a head, right? One comes up heads, the other comes up tails. So, how many total are there? There's 4. And how many could I have of differing value? 2. 2 out of 4. 1/2, which is 0.5. Like I said, I believe your homework will take either one of those, fraction form or decimal form. Okay? Okay. Let's look at example 6. Example 6 says there are 10,000 families in a certain town. They are categorized by their type of housing as follows. Okay? They can own a house. They can own, I didn't put A in there, did I? Own a house. Own a condo. Rent a house. Or rent an apartment. Okay? Now, let's talk about how many people do that. So, there are 4,753 people that own a house, or families that own a house, okay? There's 1,478 families that own a condo. There are 912 families that rent a house, and there are 2,857 families that rent an apartment. Okay? A says, what is the probability that the sampled family owns a house? Okay? Okay, so we're looking at probability of owns a house. Now, we know the bottom is the total, right? Bottom's the total. How many total families are there? 10,000. There's 10,000 different families, okay? Right? And it owns a house. The probability that out of these 10,000 different families, and I select one, what's the probability that that family owns a house? How many different families own a house? 4,753. So, you get your calculator, you type in 4,753 divided by 10,000. And once you do it, you're going to go, oh, yeah, I could have just moved that decimal 4 places to the left, because that's how many zeros there are that I'm dividing by, which gives me 0.4753. Okay, good. Nearly 50%, but guys, that makes sense. Think about it. There's 10,000 families, 4,753 own the homes. Well, what's half of 10,000? 5,000. So you have nearly half the families owning a home, and that's what you wrote down as a decimal, 0.4753. That's the good thing about statistics, is that you can reason through it. Lots of times you can look and go, that doesn't make any sense. If we'd gotten like 90.9032 or something, it'd have been like, but it's only like 5,000 out of 10,000. That shouldn't be nearly all of them, okay? So you know you did something wrong. You put something in the calculator wrong. B, what is the probability that the sampled family rents? Okay? So we want the probability that the family rents. Okay, now this one's a little different, right? But let's think about it. We know the total's the same. There's still 10,000 families that we're choosing from, right? But it says rents. And we have two different kinds of rentals going on. We have rents a house or rents an apartment. Okay, so that top number is going to be a sum of everybody that rents. Well, I've got 912 people that rent a house, plus 2,857 people that rent an apartment. How many total people rent something? Tell me that first. Good. 3,769 people rent out of 10,000. When I put that in the calculator, then I should get 0.3769, correct? Nearly 40% of the population of those 10,000 people, nearly 40% of those 10,000 people actually rent. Okay? And that kind of makes sense, guys, because if you think about it, you got nearly 50% that own the home. You've got about 40% that rent, and that leaves about 10%. It's going to be more like 15% that own that condo. I don't know who those people are, but they're not teachers. Let me say that. They're not a teacher. Okay? Okay, so not too bad. We do have a definition, an unusual event. That is the word unusual, even though it does not look like I spelled unusual. An unusual event is one whose probability is small. 0.05 is often used as the cutoff. Because, guys, that's 5%. Okay? It's such as in a job that I had before I came here, I worked in a district, I GT tested children. Okay? It is, and I ran GT testing, I tested them, I would pretty much go, yeah, you're gifted or you're not gifted. Well, one of those measures that we use, we test them, and if they fall within the top 5% nationally on a certain scale, if they fall in that top 5%, then they're considered gifted because it's an unusual event for somebody to score that high, okay? Because typically your population is not going to have more than 5% that are gifted. They're the little tail on your curve, on your symmetrical curve. They're the little tail at the end. There's the 5% at the end. There's the 5% at the other end, okay? But it's an unusual event if it's 5% or less, pretty much. So 0.05, or you get something less than 0.05, it's considered an unusual event. Example 7. In a college of 5,000 students, that's a small college. $150 are math majors. Yeah, right. Okay. A student is selected at random and turns out to be a math major. Is this an unusual event? Okay? So pretty much we're looking for, what we have to look for is the probability that the student selected is a math major. If that probability is 0.05 or less, then yes, it was an unusual event that the student that was selected was a math major. It's probably because the person that selected him was a math major and somebody construed the statistics. But anyway. Okay, what's my bottom number? What's my denominator? What's my total number of students? 5,000, good. And what are my chances of drawing a math major? 150. Good. Okay. 150 over 5,000. Put that in your calculator. What do you get? 0.03. Good. That is less than 0.05. So that means, yes, this is an unusual event. Yes, because 0.03 is less than 0.05. The simple answer is yes. Okay? Okay. Another quick definition in case they ask you about it. The empirical method. Now remember, we use the empirical method to determine what amount would fall within 1 standard deviation, and then within 2 standard deviations, and then 3 standard deviations in that population. Remember? Okay, but what was the thing with the empirical method? It had to be bell-shaped. We had to have, it only works if it's bell-shaped. Okay? Well, the empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. Okay? So, guys, pretty much what they're doing is they're mixing that empirical method with the law of large numbers. Okay? So we talked about in the law of large numbers, if we do it again and again and again and again and again and again, that experiment will approach what we call it is there's experimental probability and there's theoretical probability. Okay, so in theory, things should work out. If I flip that coin 1,000 times, I'll get heads 500 and tails 500, right? In theory, that's what should happen. Experimentally, I've got to flip it 1,000 times in order to prove what the theory says. So the law of large numbers says if I do it that 1,000 times, or I do it 100,000 times, or I do it 1,000,000 times, I'm going to get closer and closer and closer to it being 50-50 like that, okay? And the empirical method says, yeah, do that, because if you do that, then you're going to make a nice bell-shaped curve, and then we can talk about it, and that data is going to be what? Within 1 standard deviation is what, 68%, and 2 standard deviations is 98, 99, something like that percent, and then 3 standard deviations is almost all. That's the phrase they used on the test, right? Almost all for 3. Okay? So let's look at example 8. But you know they're going to come back and say something about that empirical method in some kind of, we're going to do example 8, and then we'll take a quick break because that'll be the end of 5.1. And then when you come back from 5.1, we'll start 5.2. If we don't get to 5.3 today, that's okay. I'm going to bump it. I'll bump it to next week because I really think y'all did fairly well on the test because we didn't rush things so badly. Okay, we're going to get it done. We're going to get done what we get done. It'll be fine. Example 8. There are 10,000 voters in a city Okay? A pollster takes a simple random sample of 1,000 of them and finds that 513 support a bond issue. To support the public library, to support the public library, and 487 oppose it. Estimate the probability that a randomly chosen voter in this city supports the bond issue. Now, this particular problem deals with the empirical method, okay? So what they're doing is you have a large portion of voters. There's 10,000 voters, but what they're going to do is they're selecting 1,000 of them, and then from that 1,000, they find out that 513 support, 487 do not support, and they're going to base those findings, and they're going to tell you what the population of 10,000 people are probably going to do, okay? So they're basing their results of that 10,000 population on the 1,000 people that they pulled, okay? So they polled 1,000 of the 10,000 people, and here's what they found. And they're going to come at us and say, well, this is what the 10,000 people should do, is what they're going to say. Okay? So, we have the probability that they are going to support. Is that what we're looking for? Yes, supports the bond. We're going to say that based on the 1,000 that they pulled from. Okay? So what that does is that does affect what your denominator is. You don't know out of the 10,000, do you? You know out of the 1,000, okay? So my denominator is the 1,000. Out of the 1,000, how many support? 513, which when I divide that, you can put that in the calculator. You can just move that decimal 3 places left. That's going to give me 0.513. So they're predicting that out of the 10,000 people, about 5,000, about 50%, right? 5,130 actually are going to wind up supporting it because 513 out of 1,000 did. That's all that's saying. And that they don't tell you this, but that's using the empirical method right there. That's an example of the empirical method. Okay, take a short break.